Yeah, good morning together to our lecture in statistics. And last time we had the topic of price indices in general, and we talked about inflation, we talked about different measures of inflation, and then we talked about the definition of the so-called GDP deflator, and we did a little example where we calculated the GDP deflator, and there in this calculation I made a little mistake, because since we have to calculate what we see here when calculating the index of real GDP, there we have to calculate real GDP of time t, and then I divide it by the nominal value of t also, and this is of course wrong. I have to divide it by the nominal GDP value of the former period, and then chaining with the index of real GDP of the former period. So let's redo this, and for this we go in our Excel sheet, and then let me take this actually at first out, and this also, and then again I want to show you what we have to do in order to do it the right way. Okay, so we had calculated nominal GDP, and this is of course, if we click in here, just prices times quantity, and we have to sum up, and of course minus price times quantity. This we have here when we look at the imports, and this we copied, and so here we have the values of nominal GDP and real GDP. This is of course then prices of the former period. This we see here, 1.1 times the today quantity, 1.1 of private consumption in 2019, and so on for government consumption, for grow investment, exports and imports. So we always see that we calculate this prices of the former period times quantity of the actual period, and then we just also copied this down here. And then in order to get the nominal index, this is then quite easy, because we have to take only the proportion of 21.88 over 17.7 times 100, since we say that 17.7 equals 100, which number equals then 21.88. So let's redo this. 21.88 over 17.7 and times 100. So this we have here, and then, okay, not 100, we have to take the 100 from the buff if we want to copy this. So times this one, and then we can go downwards. Let's also put this here. It former, oops. Let me see if this is now correct. Times this, and this is this times this, and so on. Then real index, and there we have to go here in our formula. So let's redo this. So it is of today, in our case, the first is 2019 divided by nominal GDP of the former period. So here our T minus 1. So in this case, then we have to calculate real GDP of today in 2019 over GDP, nominal GDP of the former period, and now chaining with the index of the former period, and 2018 we took as base, so we just set it as 100, and then we can move this down, and then we go to the definition of GDP deflator, which is just defined as nominal GDP over real GDP index times 100. So this one over this one times 100, and in this case we obtain then these values of GDP later, and here we want then the so-called wholesale price development, so the price development of the whole economy, and then we take growth rate of GDP deflator, and this will be, of course, change 115 minus 100 divided by the former value of 100, and then we obtain our price development in general. Let's also take this as percentage, and with 2 digits, and hopefully this will be now the right one. Okay, because the last time I just divided, if I remember it right, index real GDP over nominal GDP of the same period, which is of course wrong. Okay, then we will go further in our lecture, and then we also want to just calculate the Laspea, Paasche, and Fisher index with a very easy example where we have just two goods, A and B, and we have the price development and the quantities just using the definition of Laspea, Paasche, and Fisher index. So let's take this also Axel and das pair Page and Fisher. Put this in here and oops, for this we just go to the definition. There we had the last pair index, and this was the price of the basket in 2015 and 2016, and we will take the prices of the following year, multiplying this with the quantity of the former year. So this is, so to speak, forward-looking in prices. And for this, we then obtain let's take in here the last pair index. Yes, you can still see it. Take a small format. There we have it. Sorry. There. But we have then the same format. Page and Fisher. So here, what do we have to do again? Taking quantities of the former year times prices of the following year. So we obtain equals 2.5 times 20 plus 1.8 times 2, and the partial index, this would be then the other way around. We would calculate in this case the cost of the basket in the following year with prices of the former year. For this, we then obtain, in our case, where we are, oops, this is too fast. I'm looking up the Fisher index. Oops. So in the partial index, then we have, of course, to calculate then this value of the basket we have just calculated relative to the basket where we calculate prices times of the actual year times quantities of the actual year. So sorry, then we need, of course, also 2 times 20 plus 3 times 2, and this we have to take then the proportion equals 53.6 over 46. So we would have then a partial index of 1.16, last pair index of 1.116, and going to the partial index, we take this the other way around. Their prices again of the former year 2015 times quantities of the following year, and this has to be compared with prices of today times quantities of today. So in this case, we take here 2.5 times 15 plus 1.8 times 6, and here we take then the quantities of today, where we have it, that you see it, times the prices of the former year, so just the other way around. So quantities of today 15 now times prices of the former year plus now the 6 times our 3, and this we also have to calculate the proportion. This over 48, and at least then, since, and this I also gave you here on this slide, that in general we can say that the last pair index over its estimates due to substitution affects the general increase of the price level, while the partial index would more or less underestimate the increase of the price level, and therefore one invented also an average of these price level, and this is called then the Fisher index, and the Fisher index is defined just as the geometric mean of the partial and the last pair index. So we take the product and calculating the square root of both. So we end up with square root up of 1.16 times 1006, and this would be then the geometric mean, and here we see also that 1.08 is more or less in the middle between the last pair index and partial index. Okay, but this is nothing else than just using the definition. And with this, I think we ended now our first topic of time series analysis. We looked at in our actual years situation with inflation rates of 10% and more of price developments, and how we measure prices, and what are the difference between price indices, and what are the difficulties by using these price indices. Okay, so now we want to switch to in my eyes very interesting topic, because using the price indices, this is a description of the situation as it is, but for economic decisions, for market decisions, for the managers out there in the companies, well, we have to do something what we call forecasting, that we want to look in the future. And I will give you some standard methods how to use data and in order to obtain a quantitative forecast of time series. So what we want to do now is that we start with our topic forecasting. Let's switch to black again. And well, anecdotally, I have two quotes for you, and one is from a very famous physicist, Niels Bohr, and he should have said that prediction is very difficult, especially if it's about the future, just with a smile. Or if you take Winston Churchill, and he should have said that do not believe any statistic that you haven't forged by yourself, which just means, well, you can take a data set and just calculate and recalculate, and then you get out of it what you want. And I think these two quotes are, with a smile, still quite important, because of course we are always averaging something, and then of course it is possible that you always get out of the data the answer you just want to have. And it is up to you that you do it and at its best way, in an objective way, that you manipulating these data, and not only you are manipulating the data that you get the answer you just defined before you started your calculation. Okay, so let's have a look in general how data can look like. And for this, maybe we have a data series of revenue in quantities, and it looked like this. And if we have a deeper look at this time development, then maybe we can say, just looking at the data, looking at the diagram, and this is one thing I recommend for you, that you should always have at first just a look at the data, how it is moving in time. And if you look at a data set like this, then we maybe can say, well, it seems that the data is becoming larger and larger over time, more or less, so that maybe we can identify within this data something like a general trend on average. And for this, it would be then, for longer time forecasting, very interesting if you could identify a long-term trend for, let's say, forecasts for the next 3, 4, or 5 years, when you are taking data for the revenue of your company. But also, what we can see quite often in economic data is that we have some pattern which looks like a cycle, so maybe like a sine function. And also then we try to identify how long would be the period of this cycle, and what will be more or less the maxima and minima of this cycle, and without looking at the long-term trend, so that we can split more or less the data in this long-term cycle, in this long-term trend, and maybe we can then also identify some kind of a cycle. And then we more or less zoom into the data, and what we maybe also can identify is maybe something that we just heading from within T1 to T4, that we just see something like this here, that we are moving up, down, up, down, up, down, up, down. And if we maybe say that we have here data, quarterly data, so taking time t from 1 to 4 would then mean that we have data within a year. So from spring to summer to autumn to winter. And maybe there is also, similar to this longer term cycle, that we have some seasonality, which depends on some pattern within a year. And so this we call then a seasonal fluctuation. And hopefully we also can identify something like this, which is a fluctuation within a year, while maybe this is a fluctuation over 3 or 4 years. This you also can quite often identify with the business cycle, and the period of the business cycle is even quite often a bit longer, so between 5 to 10 years. And then, of course, our world is not a totally descriptive world, it's not a totally static world. And at least, of course, we will have always in economic data also some random component which we could not explain via, for example, a long-term trend, a business cycle, or seasonal fluctuations. So what we sometimes want to try is to split our data within these 3 more or less deterministic and 1 random component. And this we will do with a little example. So what we just want to do now is, well, let's try to create a series composite of a trend, cyclical, seasonal, and random data. And for this, we also want to go into Excel. And did I have this in my forecasting? This one not. Where did I have my Excel file? Nope. Where is it? No. this one. Oh. Otherwise, we have to try it together. So then let's start from this. So we take some time t, start at 0 equals 1 plus 1, and let's take roughly 50. You see this still? Yeah. So, and then let's create a trend component. So how can we obtain a trend component? Well, what would be the mathematical function which we use if you want to create a long-term trend with constant growth rate? What would you think? What can we do? Do you have an idea which kind of function we can use? So within here we would have our growth rate, and let's start with a growth rate of 0.1, and then, for example, we can use the form of an exponential function of growth rate times time. And then we can go down, up. I think I created 50, 45, or let's go to 40. Oh, I have to fix, of course, here my growth rate. And this would be then our trend data. And in order to move this trend up and down, we can also add a constant, let's say a, at this part, and let's start with just 2, for example, and then we can add this 2, just multiplying our trend with our 2 times, and we also have to fix this with dollar, and then every value will be doubled. And let's see, oops, let's take this back. If we want to look at this data, we of course obtain in here our and this one we need time. Okay. And here, oops, this one we have to. We don't need. And so we have here more or less our long-term trend data. Hi. And yeah, now we want to move to our cycle. And yeah, for this cycle, of course, then we can use in general the function of the sine. And yeah, maybe you know from school that using the sine function that you have one full period taking from 0 to 360 degrees or from 0 to 2 pi. So if we want to have then a cycle which corresponds to t moving from 1 to 40, we have to divide then our 2 times pi by the total period of, let's say, 40 days or 40 months, something like this. Therefore, I just put in here another column, and first we need pi in Excel 1.34, and in order then to obtain after 40, then we have to use equals this one divided by 2 times the full period of pi, and oops, again we have to fix this, of course, with the value of pi. No, what did I do wrong? This is fixed. Uh, now there's again some mistake in my formula. So what do I need? I need 2 pi in the end, and oh, the other way around, sorry. Oops. Of course, our value of this divided by 2 pi, and this has to be fixed. Mm, 40, no. I have to end up that 40 equals to pi. Yes, no. This is right. And then in order, as we looked at this data here, that we are also interested in the maxima and minima of our cycle, we can also introduce some constant in front of our cycle. So let's take, for example, here also a value of 3. Afterwards, we can play with these values. So this one, fixing, times sine of And this is now our value for t, since we want to end up with our period after time t equals 40. And then $45. And let's put this time also in here. So this would be the cycle data. And this would be this. And the name is cycle. And here you see that our trend data is much higher. So in order to have, more or less the same magnitude, so let's set down this parameter to 1/2. And then you see here that this is more or less our cycle. Let's even damp this to 0.2. And then you have here your trend data, and this would be your cyclical data. So what else? If we interpret our T as first quarter, second quarter, third quarter, and so on, then we could say that we want to create seasonal data. And for this seasonal data, let's start that we maybe have, depending on the weather, take for example the construction sector, that you do not build that much during winter time, and you are building more houses during the summertime. So seasonal data would then be maybe something which looks like this here, that we are moving down at T1, which maybe is winter. So again, let's start with 0, and then maybe minus 0.5. Then during spring, we are moving up again, maybe 1.2. And even going up a little bit, like this pattern, this small upwards trend, so 1.4, and then this pattern should be repeated every year, so every 4 quarters. And this then we just copy down to t is 40. Oops. This should work now, up to 40. Yes, and this last data point. So since I started my time series from at time t is 0, of course, then I have, if I go to t is 40, 41. data points. So then let's add also here our seasonal data. Yep. Add our seasonal data here and putting in our data. See, and then you see here more or less we have something, as I showed you before, a seasonal pattern. Of course, then we don't know what will be in the future, what will happen, and therefore we have also something like a random variable, and for this in your software package you quite often have just some function which creates for you random data, and this we have also in Excel, and in German this means Zufallszahl. There we have it. Yep. So there's one L to match, two L's. And now you see that this function just gives you a random number between 0 and 1. And yeah, for this also, if we want to have this random component larger or smaller, we also multiply this random number, maybe here with some constant, and let's start maybe with 0.5 for our random component. So put this in here, again fixing it, and multiply this. And maybe you also want to have this random component to fluctuate just above and below 0. And for this, we can also add here another function that we just say if this random number is smaller than 0.5, it should be negative, and if it is higher than 0.5, it should be positive. So let's put in when then I need at first, actually we can leave this component today out, and let's just use this as our random variable. So, and then 0.5 is, I think we still see it then in this data series. Actually, you have to be careful in Excel. If we then again press enter, if you look at this here, oops, if I go into the cell and pressing enter, this was then because I have here 0.5, this we have to our 0.5. So now you have seen, if I go into the cell, pressing enter again, then always your program recalculates the random variables. So I will just copy these numbers and copying this as values here. And then I have here my fixed values I created at the first as the first time series. So then move this one here. Just up. That's not working. Hopefully this one, and so putting this back. No, it's not possible. So these numbers are then fixed and they are not always changing. So this will be then our fixed random numbers. And we will put all this time series into our diagram. So this would be then the random component moving from here down to t is 40. And here you see this as the small yellow line we have here. Well, maybe let's move up this a little bit. So we take as a constant here 1. And then again we have to copy this one and copy it with our value function here. And then you see that the fluctuation is maybe half of the seasonal data, and the fluctuation of the seasonal data is maybe half of our cyclical data. Well, I think still the trend is moving up very fast. So we reduce just the growth rate. Let's go to 0.02. Now this is too much. It's 0.05. A bit more, 0.07. Maybe something like this. So this would be then all our components we have. And in the end, of course, then we start to add up all our 4 components: the trend component, the cyclical component, the seasonal component, and the random component. So let's say this is then total. And we just add up these data components. Trend data is this one plus the cyclical data plus the seasonal data plus the fixed random data. Move this down. Down to 40. And then we put in the total. Let's say our cyclical data is now in their maxima and minima quite large. Therefore, let's dampen maybe the cyclical data also a little bit. And now we put in our total data series. And this one here. And this would be then our total data, the blue line. Let's have a look only at the blue line. Just skipping trend data, cyclic data, seasonal data, and random data. And this would be then our total data. Yeah, maybe the trend data should be more dominant. So now, well, then let's go back with a higher. Oh no, not a growth rate. This was 0.27. Maybe we can just increase our constant. Yeah, this looks maybe a little bit better. And so this could be then a time series, as I introduced it already, of revenue. And yeah, what I want to do with this exercise here, that we just did it the other way around. So we started with the trend data, then we added the cyclical data, seasonal data, and the random component. And of course, in practice, it is your task to go the other way. Because if you are in your company, then you see that over the last 10 years, this was the time development of maybe your profits or your revenue. And then it is your task that you see that, yeah, you have, of course, some random fluctuation in your data, that you are able to identify, okay, it seems like that we have here some periodical data in the long term with a period of maybe 5, 6, or 7 years. And then it will be really interesting, you in your enterprise, that you know, well, I have maybe due to some market structure for my enterprise that every 3 years I will have a maximum in profits, and then it's going down again from our historical data, that you really can identify the length of this period. And of course, for the long run, you see, fortunately, my company is in general increasing. So in general, I see that profits go up, and then you want to identify this number here, especially a growth rate. And here we introduced a growth rate of 7%. And this long-term trend, this growth rate, is of course, yeah, very important for your longer-term investment decisions. Because out of this growth of profits, growth of revenue, you have to pay for your investment in general. And then, of course, if you have some seasonal pattern, this you also want to identify, that you are not surprised that within a year, maybe during summer, if you are in the touristic sector, that during summertime, not very surprisingly, your profits will go up, and that you also identify the magnitude, how much will go your profits in general going up during summertime. And then at the end, you are left with your random component, and this, that you identify this random component, and maybe with some management decision, you can reduce the magnitude of your random component, that you in the future can better forecast where will be your company tomorrow. Yeah, I think it is also quite interesting when we just started the other way around, which kind of functions we see behind our components, and this will be, of course, in general, the exponential function for trend data and sine or cosine functions for cyclical data. Okay. Then let's take this picture here and we put it in our presentation. This one, where is it? Here. And this one here. Okay, and that of course I am coming from the macro side, and so I just give you an example, and maybe you have already seen this, where you have actually, of course, a pattern like this in practice, and this is, of course, for example, the pattern of unemployment. And unemployment data you see here within a year, you have this repeating pattern. This is, yeah, so to speak, the personal cycle that mostly the human resource managers, that they will hire in general people in spring and in autumn due to educational cycles, because quite often school is ending in summer and then the young people will start to work in autumn. And then maybe also we see here some longer term trend. Here this is data from the reunification of Germany, and then you see maybe we have a long-term trend getting higher and higher unemployment rates until the year 2000. So this will be then, due to the economic performance, not the best time we had in Germany. Oops. And also you see here maybe something like a business cycle. And yeah, the end then, since the financial crisis, which we have here, this is more or less called the miracle of labor market data in Germany, that we almost, yeah, have no cyclical component anymore inside here, but only that the unemployment rates have only one direction, going down and down and down, and also only we have this just little period where we got higher unemployment rates during the Corona crisis, but then right now we are again at a situation which we call for Germany more or less full employment, but it will be really interesting what will happen here again in the future. And I suppose that if the crisis is coming, that we will see here also again some cyclical data in the labor market in Germany. Okay, so this general example for the introduction, and then in the following time we will take also here a little example let's say again, we have the development of revenue during the last years with quarterly data. And now we are interested how could we make a good guess for the future. So if we want to forecast the next quarter, so what will happen in 2023 in the first quarter, and of course maybe in the whole year, which we will see the next time. And for this, we will then take some different methods of making a simple forecast of this time series. But I think we are almost done in time. And then let's start with plotting the data and then taking the simple forecast we have. But actually, there are some economic fields where this is more or less the best forecast you can make, because the simplest forecast is maybe something like the weather forecast. How will be the weather tomorrow? And then you just look out the window and you say, well, my forecast is the best, or the weather will be tomorrow the same as today. And when I plot here the data, you can think of an economic field where actually we assume from the general framework that this simplest forecast you can make is, of course, more or less the best forecast you can get. Okay, so put in the data and the second part here. And again, just mark the data and create the diagram. And then you see again, I more or less created here a time series which has some kind of a long-term trend. Maybe you see also some cycle here and maybe also some seasonal pattern within this data. And maybe forecast here 2023 Q1. And the simplest forecast would be then if revenue in the last quarter of 2021 would be 510 million, then the simplest forecast would be just repeating this value. Let's take this one in red. So, and then for today, my last question. Maybe you had already some other lectures and in which very important economic field this really simple forecast method, just repeat the last data point, is more or less the best you can get. What do you think? Do you have an idea? Well, actually, this comes out of the assumptions you make if you have a totally competitive capital market. Because then the assumption is that, let's for example say within the stock market prices or with an index of stock market, so the DAX or the Dow Jones, every information you can get you see within these prices. And then we see from the historical data that more or less the fluctuations you see in stock market prices just represent more or less a Brownian motion. And if you have a Brownian motion, so a totally random fluctuation, then actually this is a stochastic process where you say that the expected value of tomorrow is just the value of today. So actually this is the assumption which you make if you say that I have totally competitive capital markets. Well, we see it in stock markets, but of course there are many managers throughout the world which try to beat the market, but this is quite hard, and where you also see that this assumption is quite good of a random walk in data is also in currency markets. Okay, so then this for today, and I will end the recording.